Welcome to the Sleepless Scientist, a place where the soft hum of science accompanies you into the quiet hours of the night. This is where curiosity finds a calm rhythm, and the mysteries of the universe unfold not to keep you awake, but to guide you gently toward rest. Tonight, as the stars outside shimmer in patient silence, we will explore a question that has haunted humanity for centuries. A question that transcends borders, beliefs, and even biology. Are we alone in the universe? What scientific evidence exists that may point to the possibility or impossibility of alien life? Thank you for watching this video. And if this journey into the cosmos stirs your mind more than it soothes, we sincerely apologize for any lost sleep. If you enjoy this quiet exploration, please like the video, share it with others, and leave a comment telling us where you're listening from and what time it is for you. Now, let's settle in as we begin this tale of distant worlds, unspoken signals, and the search for life beyond Earth. Throughout recorded history, humans have gazed skyward with questions too vast for any single civilization to answer. From ancient Babylonian star maps etched into clay, to Galileo's trembling observations of Jupiter's moons, the night sky has always provoked awe and suspicion. But it is only in the last century that we've had the tools to pose the question of extraterrestrial life within the framework of science. This pursuit is no longer relegated to speculation or mythology. It is now anchored in data, telescopes, spectrometers, and digital archives cataloging the observable universe. The Milky Way galaxy alone is estimated to contain between 100 and 400 billion stars. Recent estimates from NASA's Kepler mission suggest that, on average, each star in our galaxy hosts at least one planet. That brings the potential number of exoplanets in the Milky Way to over 300 billion. Among these, it is now believed that tens of billions may reside within their star's habitable zone, the region where conditions may allow for liquid water, a critical ingredient for life as we know it. One of the first serious scientific efforts to detect extraterrestrial life came in 1960, when astronomer Frank Drake pointed a radio telescope toward to sun-like stars and listened for signals. This effort, known as Project Ozma, was modest and yielded no evidence. But it ignited the field of SETI, the search for extraterrestrial intelligence, and inspired a wave of subsequent radio surveys. To date, SETI researchers have scanned thousands of star systems, while no confirmed signal from an alien civilization has been detected. The absence of evidence does not equate to evidence of absence. As detection technologies have improved, so too has our understanding of planets outside our solar system. In 1995, astronomers detected the first confirmed exoplanet orbiting a sun-like star, 51 Pegasi b. It was a gas giant, unsuitable for life as we know it. But the breakthrough opened the floodgates. As of now, more than 5,600 exoplanets have been confirmed, with over 4,000 additional candidates awaiting verification. Among these, hundreds are considered Earth-sized and reside within their star's habitable zone. Perhaps the most compelling candidates are those with similarities to Earth in terms of size, composition, and distance from their host star, planets. Like Kepler 4.5 to be located about 1,400 light-years from Earth, have fueled imaginations due to their Earth-like features. However, even if such planets exist in favorable conditions, they still present an enormous challenge in terms of direct observation. The faint light from these distant worlds is often drowned by the glare of their host stars, making detailed analysis extremely difficult. Yet progress continues. Spectroscopic methods now allow scientists to analyze the composition of exoplanetary atmospheres by observing the way starlight filters through them. This technique has already been used to detect water vapor, methane, and even possible biosignature gases such as phosphine, though each finding is subject to intense scrutiny and ongoing debate. For example, in 2020, astronomers announced the detection of phosphine in the atmosphere of Venus, a chemical that, on Earth, is primarily produced by biological processes. The discovery ignited global discussion, though subsequent studies have questioned the accuracy of the data. Still, the moment marked a turning point, where the possibility of alien microbial life was no longer confined to the realm of distant exoplanets, but extended to our own solar system. Closer to home, the search for life has focused intensely on Mars, Europa, and Enceladus. Mars, with its dry, dusty landscape, has long been considered a candidate for hosting microbial life, either in the past or perhaps even today, beneath its surface. The Viking missions of the 1970s conducted biological experiments on Martian soil with ambiguous results. Decades later, NASA's Perseverance rover, currently exploring the Jezero crater, is tasked with searching for signs of ancient life, collecting samples that will eventually be returned to Earth. Europa, one of Jupiter's largest moons, presents another compelling case. Covered in a thick shell of ice, it is believed to harbor a vast subsurface ocean. The presence of liquid water, combined with tidal heating from Jupiter's gravitational pull, suggests that conditions suitable for life could exist beneath the icy crust. In 2016, the Hubble Space Telescope observed plumes of water vapor erupting from Europa's surface, offering a tantalizing glimpse into its hidden ocean. Saturn's moon Enceladus shares many of Europa's features. It too possesses a subsurface ocean, and it has demonstrated geysers of water shooting out from its southern pole. The Cassini spacecraft flew through these plumes, detecting organic molecules and salty compounds. Though not definitive evidence of life, such discoveries build a cumulative case for the potential habitability of these alien environments. Outside our solar system, the diversity of exoplanets defies expectation. Some are massive gas giants that orbit their stars in just a few days. Others are rocky super-Earths with atmospheric compositions that suggest dynamic weather systems. Among the most promising methods of identifying habitable worlds is the search for Earth-like spectral fingerprints. Combinations of gases such as oxygen, methane, and carbon dioxide that, if found together, may indicate biological activity. In 2015, researchers found an intriguing anomaly known as Tabby's star. Its unusual dimming patterns led some to speculate about the presence of a massive artificial structure, such as a Dyson sphere. While natural explanations, like clouds of dust or cometary fragments, are more likely, the event highlights the kinds of astronomical puzzles that could hint, however faintly, at advanced civilizations. Moreover, the mathematical argument for alien life continues to gain strength. The observable universe contains an estimated 2 trillion galaxies, each with billions of stars and planets. Given these numbers, many scientists argue that it is statistically improbable that Earth is the sole cradle of life. This reasoning echoes the famous Fermi paradox, which asks, if the universe is so vast and old, where is everyone? Various hypotheses attempt to address this question, ranging from the self-destruction of civilizations to the idea that advanced life intentionally avoids contact with younger species. A growing body of research also explores the concept of life that is fundamentally different from Earth-based biology. These hypothetical life forms might be silicon-based instead of carbon-based, or they might rely on solvents like methane instead of water. Saturn's moon Titan, with its methane lakes and frigid atmosphere, has become a focal point for such speculation. NASA's upcoming Dragonfly mission aims to land a rotorcraft on Titan to explore its complex organic chemistry. Despite decades of searching, the scientific community has yet to find conclusive evidence of alien life. But the search itself has transformed our understanding of the universe and our place within it. The question is no longer a fringe pursuit. It is one of the most profound scientific inquiries of our time. And while the answers remain elusive, The possibility that life may exist beyond Earth continues to inspire missions, telescopes, and theoretical frameworks across every continent. The silence of the cosmos is not proof of emptiness, but rather an invitation to listen more carefully, to observe more closely, and to consider the vastness not as an obstacle, but as a canvas for discovery. The pursuit of alien life is shaped not only by observations and instrumentation, but by the frameworks we build to define what life is and how it may arise. On Earth, life is characterized by properties such as reproduction, metabolism, growth, response to stimuli, and adaptation through evolution. However, this definition may be too narrow when applied to potential life forms that evolved under alien conditions. Life as we know it may be merely one branch of a larger biological tree that spans unknown chemistries and environmental baselines. Thus, scientists often distinguish between life as we know it and life as we don't know it, with the latter being speculative but critical for expanding the search beyond terrestrial assumptions. Astrobiology, the interdisciplinary science that studies the origins, evolution, distribution, and future of life in the universe, forms the backbone of this exploration. It synthesizes data from biology, chemistry, planetary science, and astronomy. Within astrobiology, researchers investigate prebiotic chemistry, the set of chemical processes that may have led to the emergence of life on Earth. These findings offer potential analogs for what may occur elsewhere in the cosmos. Hydrothermal vents on the ocean floor, for example, provide extreme yet stable environments where life thrives without sunlight, driven instead by chemical energy. Such ecosystems serve as models for similar environments that could exist under the icy crusts of Europa or Enceladus. In recent years, advances in computational modeling have enhanced our ability to simulate planetary climates, atmospheric compositions, and geological processes. These simulations allow scientists to predict which exoplanets are most likely to maintain surface water and stable temperatures. Observatories like the James Webb Space Telescope have begun targeting such worlds, searching for chemical imbalances in their atmospheres that might hint at biological processes. For example, if a planet's atmosphere simultaneously contains oxygen and methane, two gases that readily react and eliminate each other, it may suggest that some ongoing process, possibly life, is replenishing them. Another emerging tool in the search for alien life is the study of technosignatures, indirect evidence of advanced civilizations. These could include unusual patterns of electromagnetic radiation, large-scale energy usage, or even atmospheric pollutants not explainable by natural processes. In 2018, researchers from Harvard speculated that a strange interstellar object named Oumuamua, which passed through our solar system in 2017, might be an artificial probe, though natural explanations remain dominant in the scientific community. Such hypotheses underscore the growing willingness to entertain a broader range of possibilities when interpreting unexplained phenomena. Within our own solar system, the study of meteorites offers another line of inquiry. Certain meteorites, such as the famous ALH84001 found in Antarctica, have been proposed to contain microscopic structures resembling fossilized bacteria. The claim remains contested and lacks consensus. It sparked a wave of research into how biological signatures might be preserved in spaceborne rocks. Additionally, some meteorites contain amino acids, the building blocks of proteins, suggesting that the ingredients for life may be widespread in the cosmos. Panspermia, the hypothesis that life may have originated elsewhere and traveled to Earth via comets, asteroids, or interstellar dust, adds yet another layer of complexity to the discussion. While still speculative, panspermia is supported by the resilience of certain extremophiles, organisms that can survive harsh radiation, vacuum, and temperature extremes. Experiments aboard the International Space Station have demonstrated that some microbes can endure prolonged exposure to outer space, lending tentative support to the idea that life could travel between celestial bodies. In addition to searching for life in the present, scientists also investigate the conditions under which life might arise in the future. Planets orbiting long-lived stars such as red dwarfs could offer billions of years of environmental stability, far exceeding Earth's window for habitability. Red dwarfs make up approximately 70% of all stars in the Milky Way, and many of their planets reside in the habitable zone due to the star's low luminosity. However, red dwarfs also exhibit intense solar flares that may strip away planetary atmospheres. The balance between these factors determines whether such systems are suitable for sustaining life. On Earth, life has demonstrated remarkable adaptability. From bacteria thriving in radioactive waste to organisms living beneath Antarctica's ice sheets, biology on this planet is extraordinarily resilient. These examples are crucial because they broaden the range of conditions we consider habitable. In effect, Earth serves as both a template and a testing ground for evaluating the plausibility of alien ecosystems. The discovery of entire ecosystems that derive energy from sulfur or ammonia rather than sunlight reshapes our expectations for where life can flourish. Another fascinating avenue is the analysis of isotopic ratios, which may serve as potential biosignatures. On Earth, living organisms preferentially use certain isotopes during metabolic processes, leading to detectable shifts in isotope abundances. If similar shifts were observed on another planet or moon, they could provide indirect evidence of biological activity. Scientists are currently refining instruments capable of detecting these subtle differences, potentially adding a powerful tool to the search for extraterrestrial life. The implications of discovering alien life, whether microbial or intelligent, would be profound. At the biological level, it would expand our understanding of life's potential and resilience. At the philosophical and cultural level, it would redefine humanity's place in the cosmos. Some scholars argue that even the discovery of microbial life elsewhere would constitute a second genesis, suggesting that life is a natural outcome of planetary processes rather than a singular anomaly. Others contend that the psychological and sociological impacts would depend heavily on the nature and context of the discovery. Government and private organizations alike continue to invest in the search. NASA's missions to Mars and the outer solar system, ESA's planned life detection probes, and China's growing planetary exploration program all signal a rising global interest. Meanwhile, private entities like Breakthrough Listen are conducting expansive radio surveys, analyzing petabytes of data for signals of non-human origin. These efforts are not only technological achievements, but also cultural expressions of a collective desire to understand whether we share the universe with other sentient beings. Public interest in the topic remains high, and occasional government disclosures have added intrigue. In 2021, the U.S. Office of the Director of National Intelligence released a report summarizing over 140 unexplained aerial phenomena encountered by military personnel. While the report did not confirm extraterrestrial origins, it acknowledged that many events lacked clear explanations and warranted further investigation. The disclosure revitalized discussions about the potential for intelligent life and the role governments may play in studying or concealing related data. As the search continues, skepticism remains essential. The scientific method demands rigorous testing, peer review, and replication before accepting extraordinary claims. False positives, observational errors, and biased interpretations must be carefully ruled out. Yet even with these constraints, the momentum behind the search for alien life grows stronger each year. It is fueled not by fiction, but by data, probability, and the persistent desire to understand our place in a vast, ancient universe. We have already discovered that life can thrive in places once thought uninhabitable. We know that organic molecules are common in space, that planets are abundant, and that water exists in many forms across the solar system and beyond. Each new discovery narrows the gap between possibility and probability. While we may not yet have found definitive proof, the signs are accumulating like distant signals in the night, faint but unignorable. Beyond the realm of observation lies a deeper set of questions about the emergence, persistence, and detectability of life in a universe governed by the unyielding laws of nature. If life exists elsewhere, is it widespread or incredibly rare? Is it bound by time and vulnerability, as on Earth, or does it adapt beyond comprehension, thriving in forms we cannot recognize? Scientific inquiry navigates these uncertainties through models that combine astrophysical, biological, and environmental data to simulate scenarios under which life might not only arise, but also survive and evolve under alien conditions. Central to this exploration is the concept of habitability, a term that goes beyond the simplistic idea of Earth-likeness. Habitability involves a complex interplay of factors: the presence of energy sources, the availability of essential elements, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and environmental stability over geological timescales. The traditional habitable zone is often defined as the orbital region around a star where liquid water could exist, is increasingly understood as only one aspect of a planet's potential for life. Subsurface oceans, geothermal activity, atmospheric retention, and magnetic shielding are now considered equally vital. The study of atmospheric biosignatures has emerged as one of the most promising approaches in this field. Biosignatures are substances, such as gases or combinations of chemicals, that might be indicative of biological activity. For instance, Earth's atmosphere contains a stable mixture of oxygen and methane, which coexist only because biological processes continually replenish them. Without life, oxygen would bind with surface materials and methane would degrade. Under sunlight, thus, the presence of such disequilibrium on another planet would raise compelling questions about the mechanisms maintaining it. Current and upcoming telescopes are equipped to search for such signs. The James Webb Space Telescope, launched in December 2021, is already analyzing the atmospheres of distant exoplanets using transit spectroscopy. When a planet passes in front of its star, some of the starlight filters through its atmosphere, leaving faint spectral fingerprints. By measuring how different wavelengths of light are absorbed, scientists can deduce the presence of gases like carbon dioxide, water vapor, and potentially more complex molecules. Though the signals are weak and require careful interpretation, the method holds promise for detecting planets with biological or prebiotic chemistry. In parallel, the study of extremophiles continues to inform our assumptions about the limits of life. These organisms, which survive and thrive in environments of extreme heat, cold, salinity, acidity, radiation, or pressure, suggest that life elsewhere might not only exist but flourish under conditions once thought impossible. From bacteria in boiling hydrothermal vents to fungi living inside rocks in Antarctica, extremophiles redefine the boundaries of habitability. Some have even survived exposure to the vacuum of space, radiation, bombardment, and microgravity. These capabilities suggest that if similar forms exist elsewhere, they may be resilient enough to endure interplanetary or even interstellar conditions. Investigations into Earth's deep biosphere have also revealed thriving microbial ecosystems several kilometers below the surface, isolated from sunlight for millions of years. These communities rely on chemical energy derived from the breakdown of rock and water, hinting at analogous ecosystems that could exist on Mars or beneath the icy crusts of Europa and Enceladus. The presence of methane on Mars, especially in localized spikes detected by orbiters and rovers, remains an unresolved mystery. Though methane can be produced geologically, its seasonal variation hints at dynamic processes that might involve microbial life below the surface. The ethical and philosophical implications of finding alien life are also increasingly part of the scientific discourse. Discovering even microbial life beyond Earth would prompt reevaluation of concepts like planetary protection, biological contamination, and our responsibility to ward alien ecosystems. Protocols already exist to prevent Earth organisms from contaminating other worlds during exploration missions, and vice versa. But the emergence of synthetic biology and autonomous, robotic exploration raises questions about how these principles can be enforced in increasingly complex missions beyond microbial life. The question of intelligent extraterrestrial civilizations poses its own set of scientific and philosophical challenges. For decades, SETI researchers have scanned the sky for technosignatures, signals, or phenomena that might indicate the presence of advanced technology. These include narrowband radio transmissions, pulsed laser emissions, or patterns of stellar dimming consistent with megastructures. While no confirmed technosignatures have been detected, the scale and scope of the search continue to expand. Large radio arrays such as the Allen Telescope Array and China's FAST are capable of monitoring millions of stars for unusual signals. These facilities generate enormous volumes of data, which are analyzed by algorithms trained to detect patterns that differ from natural sources. Public involvement in these efforts has also increased, with citizen science projects like SETI at home leveraging the processing power of personal computers to analyze signal data. Despite the absence of confirmed results, these programs demonstrate the enduring human interest in finding intelligent life beyond Earth. The Drake equation, proposed in 1961, offers a probabilistic framework for estimating the number of active, communicative extraterrestrial civilizations in the Milky Way, while many of its variables remain uncertain. Such as the average lifespan of a technological civilization, it provides a starting point for scientific discussion. Some estimates yield high probabilities of intelligent life, while others are more conservative, suggesting that advanced civilizations may be extremely rare or short-lived. The equation's enduring relevance lies not in precise predictions, but in structuring the dialogue around testable hypotheses and observable factors. Another line of inquiry considers the role of time in the search for extraterrestrial intelligence. The galaxy is approximately 13.6 billion years old and technological. Civilizations may emerge at different times and rates. The likelihood of two or more such civilizations existing and being detectable at the same time is subject to immense variability. Civilizations may rise and fall without ever overlapping in communicative timelines. This temporal mismatch may explain the so-called Great Silence, the apparent absence of contact despite the statistical likelihood of intelligent life. Additionally, some scientists propose that alien civilizations may be undetectable by our current instruments due to their use of technologies beyond our understanding. Others suggest they may intentionally avoid detection, adhering to a form of cosmic quarantine to prevent cultural interference with less advanced species. This hypothesis, known as the zoo hypothesis, remains speculative but illustrates the wide range of scenarios considered within astrobiology and SETI. Machine learning and artificial intelligence are now playing a growing role in analyzing complex data sets generated by telescopes and surveys. These tools can identify anomalies, cluster similar patterns, and flag potential outliers for further investigation. For example, AI has been used to reanalyze archived radio data and identify previously overlooked signals, although none have yet been confirmed as extraterrestrial in origin. The integration of AI may accelerate discoveries, not only by reducing analysis time, but also by uncovering correlations invisible to the human eye. Meanwhile, laboratory simulations attempt to recreate prebiotic conditions on other worlds. Experiments replicate the atmospheric and surface conditions of Mars, Titan, and other bodies to test how organic molecules behave or how life might originate under different circumstances. These studies help refine our predictions and guide future missions in selecting promising sites for life detection. Ultimately, the scientific search for alien life rests on a foundation of incremental discovery. Each piece of data, each anomaly, and each new technique contributes to a broader picture of cosmic potential. It is a process that requires patience, precision, and a willingness to confront the unknown without leaping to conclusions. The question is not merely whether life exists elsewhere, but how we would recognize it, how we would prove it, and how we would respond. The search for alien life is not a quest for spectacle, but for knowledge. It is a quiet, deliberate unraveling of possibility woven into the vast and silent structure of the universe. Whether life is abundant or vanishingly rare, the pursuit itself has already transformed science, inspired generations, and reminded us that the cosmos may hold answers far greater than any we have yet imagined. To grasp the full scope of the search for alien life, one must consider the diversity of planetary systems revealed through astronomical surveys. Observations from missions like Kepler, TESS, and the European Space Agency's Gaia have radically altered our understanding of planet formation and distribution. Exoplanetary systems are often wildly different from our own, featuring planets in eccentric orbits, hot Jupiters spiraling close to their stars, and terrestrial planets locked in gravitational resonance. These discoveries expand the known parameters of planet habitability and force scientists to revise assumptions based solely on our solar system's architecture. Among the thousands of known exoplanets, the concept of the Earth analog remains a central focus. These are planets that approximate Earth in size, composition, and position within the habitable zone of their stars. Yet even among this subset, critical variables such as atmospheric composition, magnetic fields, axial tilt, and rotation rate remain largely unknown. A planet's ability to sustain life is deeply dependent on long-term climate stability, plate tectonics to recycle nutrients, and a magnetosphere to shield against harmful cosmic radiation. Without such features, even planets within the habitable zone may be sterile. The influence of stellar activity is another important factor. While red dwarf stars offer longevity and stability over trillions of years, they also emit frequent and intense flares that can erode planetary atmospheres. Young stars of all types are particularly active, and planets orbiting close to them, where the habitable zone often lies, are vulnerable to stripping effects that remove essential volatiles. The discovery of Proxima Centauri b, an Earth-sized planet orbiting the closest star to our Sun, sparked excitement. But its exposure to powerful stellar flares raises doubts about its habitability. Despite these challenges, the detection of potentially life-supporting planets continues to accelerate. Observations of TRAPPIST-1, an ultra-cool dwarf star system containing 7 Earth-sized planets, 3 of which lie in the habitable zone, provide a unique opportunity for comparative planetology. These worlds orbit so closely to one another that gravitational interactions may influence their climates and geological activity. Their proximity to Earth, about 40 light-years away, makes them prime targets for future atmospheric studies using next-generation telescopes. Beyond exoplanets, moons may offer more plausible venues for life. In our solar system, Europa and Enceladus remain top candidates due to their subsurface oceans, but Titan and Ganymede also draw scientific attention. Titan, Saturn's largest moon, has a thick atmosphere rich in nitrogen and methane, as well as lakes and rivers of liquid hydrocarbons on its surface. Though radically different from Earth, Titan may host exotic forms of chemistry that mirror early Earth conditions or represent a separate path toward biogenesis. The Dragonfly mission, scheduled to launch in the 2030s, will send a rotorcraft to explore Titan's surface, analyze organic compounds, and assess its potential for prebiotic or biological processes. This mission represents a shift in focus, from passive observation to active, mobile exploration in environments that challenge our definitions of habitability. Meanwhile, ESA's JUICE Jupiter Icy Moons Explorer and NASA's Europa Clipper aim to closely examine the ice-covered moons of Jupiter, using radar and spectrometry to map their subsurface oceans and analyze surface composition. Each of these missions feeds into a broader framework of inquiry, where the boundaries between biology, chemistry, and planetary science blur. One emerging area is the study of chemical disequilibrium, conditions where chemical reactions do not reach a stable state due to continuous energy input, often associated with biological activity. For example, the coexistence of oxygen and methane, or unusual ratios of certain trace gases, may signal ongoing metabolic processes. These patterns can be sought using remote spectroscopy or directly measured through landers and probes. Simultaneously, Earth remains a vital control sample in the study of life. The pale blue dot continues to reveal new extremophiles, new mechanisms of adaptation, and new biochemical pathways. Hydrothermal vent ecosystems demonstrate that life can originate in the absence of sunlight, sustained by chemical energy from the Earth's interior. Deep subsurface bacteria challenge our concepts of ecological isolation, thriving for millions of years cut off from the surface biosphere. Even atmospheric microbes have been discovered in the upper layers of Earth's skies, suspended at altitudes above the clouds. These discoveries prompt scientists to develop models for non-surface ecosystems. Life not bound to planetary crusts, but suspended in high-altitude layers or deep below icy shells. The possibility of life existing in the high atmosphere of Venus, for example, is again under investigation due to the detection of anomalous chemicals like phosphine, although the results remain inconclusive and contentious. Regardless of the final verdict, the willingness to examine life's possibilities in such environments represents a broadening of scientific imagination. The study of biosignatures and technosignatures has also intersected with theories of evolution and development. Some researchers argue that intelligence may not be an inevitable outcome of evolution, but rather a rare convergence of biological and environmental pressures. Others suggest that intelligence may be widespread but difficult to detect due to differences in communication methods, behavior, or even dimensional perception. If advanced civilizations use neutrino communication, quantum entanglement, or engineered gravitational waves, our current instruments might be entirely blind to their signals. The role of non-carbon-based life has also entered serious academic discussion. While carbon's ability to form complex and stable molecules makes it the backbone of terrestrial life, alternatives like silicon or even metallic-based biochemistries are being explored theoretically. Such life forms might emerge in high-temperature environments or under entirely different physical laws. They may not require water as a solvent, but instead use ammonia, methane, or supercritical carbon dioxide. While these remain speculative, they open the door to a broader search strategy that does not assume Earth's biochemistry as the universal norm. Increasingly, astrobiologists emphasize a probabilistic approach to alien life, focusing not on definitive yes or no questions, but on mapping likelihoods across a vast parameter space. This probabilistic framework guides telescope targeting, strategies, mission planning, and data interpretation. It also helps avoid anthropocentric bias by recognizing that life's expression elsewhere may be utterly foreign to human experience. In this expanding search, the concept of false positives and false negatives is a central concern. A false positive occurs when a signal mimics a biosignature but is produced by abiotic processes such as methane emissions from volcanic activity. A false negative occurs when life is present but undetectable due to observational limitations or misinterpretation. Understanding these pitfalls requires collaboration across disciplines. Astronomers must consult geologists, chemists, biologists, and computer scientists to refine detection criteria. Another key development is the shift toward international and open data collaboration. With missions and observatories generating terabytes of data per day, No single institution can process it all alone. Shared databases, public archives, and distributed computing projects now allow a global community of scientists and amateur analysts to participate in the search. This democratization of discovery increases the chances that a significant anomaly, whether a spectral fingerprint or a repeating signal, will be noticed, studied, and verified. As this search progresses, it remains tethered to the limits of technology and knowledge. Yet within those limits lies a tremendous frontier. The universe is not static, but in constant motion. Stars are born and die, planets migrate, and conditions evolve. Life, if it exists elsewhere, may be undergoing transformations we have yet to imagine. We may be early observers in a cosmos still awakening, or we may be latecomers in a galaxy where civilizations once flourished and now lie silent. Whatever the outcome, the search for alien life reveals more than distant possibilities. It teaches us about ourselves. It highlights the fragility and resilience of life on Earth, underscores the importance of planetary stewardship, and challenges us to look beyond borders, species, and histories. It is not merely a scientific endeavor, but a deeply human one, driven by wonder, humility, and the enduring urge to know if we are part of something greater than ourselves. Within the context of cosmic history, the search for alien life unfolds on a timeline that dwarfs human civilization. The Earth formed approximately 4.5 billion years ago, and the earliest known signs of life date back at least 3.7 billion years, with some evidence suggesting even earlier origins. For most of this time, life remained microbial, confined to oceans and atmospheres, gradually altering the composition of the planet. Only in the last 500 million years did multicellular life flourish, and human civilization occupies merely a fraction of the final second in this biological clock. This perspective underscores the likelihood that life, if it exists elsewhere, may most often be microbial, persistent, and ancient, rather than complex or intelligent. Life on Earth demonstrates a capacity for transformation driven by energy, flow, and environmental gradients. From cyanobacteria oxygenating the atmosphere to the emergence of photosynthesis and eukaryotic cells, evolution acts as both sculptor and survivor. It does not require intelligence to succeed, only stability, adaptability, and continuity. As such, many researchers now focus not on finding intelligent life, but on detecting planetary-scale signs of microbial or ecological activity. This shift acknowledges the scale of deep time and the rarity of technological emergence. Indeed, Earth's technological phase has lasted for only about a century, a blink in geological terms. Our radio transmissions, launched into space starting in the early 20th century, have only traveled about 100 light-years, reaching a minuscule fraction of the galaxy. The silence we perceive may not be a reflection of absence, but of infancy. Civilizations separated by thousands or millions of years might never overlap, or their signals may be too weak, too brief, or too alien for us to recognize. Furthermore, the cosmic environment presents formidable obstacles to sustained interstellar communication. Signals degrade with distance, absorbed and scattered by cosmic dust, gas, and magnetic fields. The energy required to send a clear, directional message across even a single light-year is immense. For this reason, some researchers advocate for passive listening rather than active broadcasting, a strategy known as passive SETI, which minimizes assumptions and reduces the risk of cultural contamination or unintended contact. One of the most thought-provoking aspects of this search is the potential variety of evolutionary trajectories. On Earth, intelligence arose not as a direct goal, but as a byproduct of ecological pressures. It co-evolved with social structures, language, and tool use, leading to symbolic reasoning, abstract thought, and eventually, technology. But there is no guarantee that such traits would develop elsewhere. On a different planet, under different Pressure's life might evolve toward entirely different goals: colonial structures, chemical communication, or collective cognition without centralized brains. The assumption that intelligence leads to communication may also be flawed. On Earth, countless intelligent species, dolphins, octopuses, corvids, demonstrate problem-solving, memory, and even symbolic reasoning, yet none have developed radio, technology, or global infrastructure. Intelligence alone is not sufficient for interstellar presence. It must coincide with cultural factors, material resources, and technological continuity over many generations. Civilizations may rise and fall due to war, environmental collapse, or technological stagnation before achieving detectability. This realization has led to models that explore the lifespan and self-limiting nature of civilizations, known as the Great Filter. This concept proposes that somewhere along the path from microbial life to spacefaring society lies a barrier that few, if any, civilizations overcome. The filter could be behind us, meaning life is rare, and Earth is an exceptional success. Or it could lie ahead, suggesting that advanced civilizations tend to destroy themselves before achieving sustainable interstellar presence. Understanding where this filter lies may be one of the most important questions in astrobiology. In light of these possibilities, Earth itself becomes an essential experiment. The continued survival of human civilization, its choices, sustainability, and stewardship may determine whether we ever find or become the kind of life we seek in the cosmos. Space exploration is not merely an external journey, but an inward reflection on survival, cooperation, and responsibility. Recent advances in space-based infrastructure reflect this growing awareness. Telescopes like the Vera C. Rubin Observatory and upcoming missions like LOVOIR and HABEX are designed not just to study distant worlds, but to assess planetary systems holistically, measuring star-planet interactions, long-term habitability, and signs of technological activity. These observatories will increase our ability to image Earth-sized planets directly, analyze their light with higher resolution, and potentially detect biosignatures or artificial modifications. Simultaneously, advancements in spectroscopy and photometry allow increasingly detailed study of exoplanet atmospheres. The detection of unusual compounds, such as chlorofluorocarbons or nitrogen oxides, might indicate industrial activity. These hypothetical signals, though speculative, expand the range of detectable technic signatures. Unlike biological markers, which often require specific temperature and pressure conditions, technosignatures may emerge in unexpected configurations, revealing artificial structures, altered albedos, or heat dissipation patterns inconsistent with natural processes. The concept of planetary intelligence has also emerged in recent theoretical models. It proposes that mature biospheres may eventually regulate themselves through collective feedback systems, maintaining habitability over geological timescales. If this is true, then life-bearing planets might exhibit global-scale stability in temperature, gas composition, and hydrological cycles beyond what physics alone predicts. Such regulation could be interpreted as a biosignature, or even an early form of planetary consciousness, detectable through climate modeling and spectral analysis. As observational capabilities improve, interdisciplinary collaboration becomes increasingly vital. Astrobiologists consult with anthropologists to understand cultural evolution, with linguists to imagine non-human communication systems, and with cognitive scientists to assess forms of intelligence not centered on logic or language. This holistic approach acknowledges the complexity of detecting and interpreting alien life. A signal or anomaly alone is insufficient. It must be contextualized within a framework that spans biology, culture, and systems theory. Meanwhile, public interest in extraterrestrial life continues to influence science, policy, funding, and media. Documentaries, novels, and speculative science serve as cultural scaffolding, shaping expectations and interpretations. The narratives we build about alien life, whether utopian, dystopian, or transcendent, reveal as much about ourselves as about the unknown. They inspire research, but they also require caution, lest we confuse entertainment with evidence. This atmosphere of anticipation and humility, the scientific process provides balance. Every new candidate biosignature is subjected to rigorous analysis, peer review, and debate. False leads are common, and retraction is part of progress. The road to discovery is long, nonlinear, and filled with uncertainty. Yet the persistence of the search, its expansion across disciplines and borders, reflects an enduring truth. The question is worth asking. Alien life may not resemble anything we expect. It may be microscopic, silent, or hidden beneath layers of rock and ice. It may be transient, evolving, and vanishing before we can detect it. Or it may be watching from distances we cannot yet reach. Each possibility carries weight. Each implies different consequences for science, philosophy, and society. In the end, the search for alien life is a mirror. In looking outward, we reflect inward. We calibrate our instruments not only to detect distant worlds, but to understand this one. And with each new telescope launched, each dataset collected, and each anomaly investigated, we get closer to answering the question. Not just are we alone, but what does it mean to be alive? As the search for alien life presses forward, the role of space exploration becomes increasingly foundational. Not only through telescopic observations from Earth, but through missions that physically reach out into the solar system. Robotic explorers have become our proxies, venturing into harsh terrains and extreme environments to gather data that may redefine what constitutes a habitable world. These missions serve as the sensory organs of humanity's extended gaze, translating silent landscapes into streams of information that deepen our understanding of the potential for life beyond Earth. Mars remains the most thoroughly studied target in the solar system when it comes to the direct search for life. Decades of orbiters, landers, and rovers have revealed a planet shaped by water, wind, and time. Dried-up riverbeds, ancient deltas, and sedimentary layers point to a watery past where lakes and even shallow seas may have persisted for millions of years. The Curiosity rover, operational since 2012, has drilled into Martian rocks and detected complex organic molecules, carbon-based compounds that, while not definitive proof of life, indicate the basic chemical prerequisites for biology. More recently, the Perseverance rover has expanded this mission, focusing explicitly on astrobiology. It is equipped with instruments capable of identifying biosignatures at microscopic scales, and it is collecting samples intended for return to Earth via a future mission. The idea behind this campaign is simple: to examine Martian soil and rock. In terrestrial laboratories where analysis can be conducted at levels of precision far beyond what onboard instruments allow. If life ever emerged on Mars, even if only in microbial form, the geochemical record may still preserve its signature. The question of whether Mars is currently inhabited, even in its deepest subsurface regions, remains open. Data from orbiters have revealed periodic plumes of methane in the atmosphere, which fluctuate seasonally and may originate from underground sources. While methane can be produced abiotically through geological processes, it is also a metabolic byproduct of certain microbial life forms. These plumes remain unexplained and controversial, highlighting the fine line between discovery and interpretation. Elsewhere in the solar system, the icy moons of Jupiter and Saturn offer some of the most intriguing possibilities for extraterrestrial ecosystems. Europa, covered in a thick shell of water ice, is believed to possess a global subsurface ocean, kept liquid by tidal heating from Jupiter's gravitational pull. The ice shell may be 15 to 25 kilometers thick, but beneath it lies a layer of liquid water, potentially 60 to 150 kilometers deep, more than all of Earth's oceans combined. Geological features such as ridges, fractures, and chaos terrain suggest dynamic processes that could allow nutrients to cycle between the ocean and the surface. The potential habitability of Europa will be explored in detail by NASA's Europa Clipper mission, which will launch in the coming years. It will conduct dozens of flybys using radar, magnetometry, light, and spectrometers to map the moon's structure, analyze surface chemistry, and search for signs of water plumes. These plumes, if confirmed, could offer direct access to the subsurface ocean without the need for drilling, an opportunity to sample material that may contain organic compounds or even microscopic life. Similarly, Saturn's moon Enceladus has already demonstrated the presence of active geysers ejecting material from a subsurface ocean through fractures near its south pole. During its mission, the Cassini spacecraft flew directly through these plumes, detecting water vapor, salts, simple organics, and even complex macromolecules. These findings elevated Enceladus from a cold, icy body to a compelling candidate for life. The energy from tidal heating, coupled with the presence of water and organics, creates an environment that, at least in theory, could support microbial ecosystems. These moons highlight a key shift in astrobiology from the search for Earth-like planets in the habitable zone to the recognition that internal oceans and chemical energy can sustain life even far from solar warmth. This expansion of the habitable model from Goldilocks zones to energy-rich niches reflects the adaptability of life on Earth and the growing realization that similar niches may be common throughout the galaxy. While direct exploration of exoplanets remains out of reach, ongoing technological advances are laying the groundwork for a future in which detailed study of these distant worlds becomes possible. Starshade missions, which would block the light of a star to enable clearer imaging of orbiting planets, are under conceptual development. These, combined with powerful space telescopes, may one day allow scientists to resolve the surfaces of exoplanets, analyze their atmospheres, and search for optical or thermal anomalies that could indicate life or technology. Even without direct imaging, the study of light curves, how a star's brightness changes as a planet passes in front of it, can reveal surprising details. Researchers have used these observations to infer the presence of clouds, weather patterns, and even rotational periods on exoplanets. With higher resolution instruments, it may soon become possible to detect surface vegetation through subtle color variations or to identify artificial illumination patterns that differ from natural reflected light. In parallel, the field of synthetic biology is preparing for a new role in space exploration. Engineered organisms could one day be used to detect trace chemicals, extract resources, or even terraform environments to make them more hospitable for human activity. While these goals remain distant, they raise ethical considerations about biological contamination and planetary protection. If we are to search for alien life, we must be careful not to introduce Earth life in the process, especially in environments that may harbor native ecosystems. The implications of finding alien life, especially microbial life, would be immense. It would provide the first evidence of a second genesis, demonstrating that life is not a fluke confined to one planet, but a probable outcome of cosmic chemistry. This would suggest that the universe is not only populated by stars and rocks, but by biology, dispersed, evolving, and adapting across a multitude of worlds. Such a discovery would inform fields from medicine to theology, from environmental science to philosophy. At the same time, the discovery of intelligent life, or evidence thereof, would confront humanity with questions of unprecedented scale. How should contact be initiated, if at all? What rights or considerations might non-human civilizations possess? How would global institutions respond? And would humanity find unity in the face of a shared cosmic reality, or fall into division and fear? These are not questions for the future alone. They shape policy, education, and research priorities today. Organizations such as the United Nations Office for Outer Space, Affairs have begun considering the frameworks for dealing with discovery scenarios. Think tanks and academic conferences explore the legal, ethical, and cultural dimensions of contact. These efforts acknowledge that even a distant or ambiguous signal could change the trajectory of human history. Yet, even in the absence of a definitive discovery, the search itself remains valuable. It fosters international collaboration, pushes the boundaries of technology, and inspires generations of scientists, engineers, and dreamers. It encourages humility in the face of a vast universe and wonder at our shared origins. And perhaps, most importantly, it reminds us that questions without immediate answers can still be worth asking, and that the pursuit of knowledge is its own form of meaning. As we continue to listen, to explore, and to interpret the silent signals of the stars, we participate in an unfolding narrative older than humanity and wider than Earth, whether alien life reveals itself in microbial chemistry or in the whisper of a distant signal. We are preparing not just our instruments, but our minds for that possibility. As the scientific search for alien life moves deeper into the 21st century, the frameworks we use to interpret potential discoveries have grown increasingly nuanced, integrating probability theory, planetary science, and the psychology of perception. Detection is not just about finding life. It is about proving that what we observe cannot be explained by non-biological processes. It is about demonstrating with sufficient confidence that a particular chemical signal, environmental anomaly, or technological artifact could only be attributed to life. To this end, scientists have introduced classification schemes to quantify and evaluate potential biosignatures. These frameworks account for context, including the planet's temperature, pressure, star type, and geochemical environment. One such system is the biosignature confidence ladder, a scale designed to move a potential detection from a preliminary observation to a confirmed biological interpretation. A single molecule or gas, such as oxygen or methane, is insufficient on its own. It must be assessed alongside co-occurring signals, environmental plausibility, and potential false positives. This multi-layered approach mirrors how life detection would likely proceed in practice. Imagine a planet orbiting a nearby star, where telescopic data reveals a nitrogen-oxygen atmosphere, surface temperatures permitting liquid water, and spectral hints of methane and chlorophyll-like reflectance. On Earth, such a combination would strongly imply life. But confirming this on an exoplanet would require successive observations, modeling, and the elimination of alternative explanations, such as volcanic activity or photochemical reactions. Each step would raise the probability, but no single measurement would deliver certainty. As a result, the scientific method remains the cornerstone of credibility in astrobiology. Anomalies are not evidence until they survive falsification. Hypotheses must be tested across independent lines of inquiry, and discoveries must be replicable by other instruments, teams, and methodologies. This rigor ensures that claims of alien life, should they arise, are built on foundations that withstand scrutiny, skepticism, and the weight of global consequence. One particularly compelling area of recent research involves the study of exoplanet albedos and surface biosignatures. Albedo refers to the reflectivity of a planet's surface, which can change depending on its terrain, cloud cover, oceans, vegetation, or artificial structures. On Earth, the red edge of vegetation, a distinct spectral feature due to chlorophyll's interaction with sunlight, provides a potential analog. If similar features were detected on another planet, particularly in conjunction with atmospheric oxygen and carbon dioxide, the case for biological surface processes would grow stronger. In addition to natural biosignatures, artificial signatures, also known as technosignatures, remain a parallel avenue of investigation. These include radio emissions, laser pulses, megastructures, or waste heat from industrial activity. Civilization. Generating large amounts of energy might radiate infrared emissions in quantities inconsistent with natural thermal sources. Such emissions could, in theory, be detected as infrared excesses surrounding stars. While no such signals have been definitively observed, the concept remains scientifically testable, and efforts to detect them continue. Interestingly, recent machine learning applications have been repurposed to identify previously overlooked signals in historical data. In 2023, a machine learning model applied to archived SETI observations detected dozens of anomalies. Signals with narrow bandwidths and signal-to-noise ratios inconsistent with known sources of interference, while further analysis attributed many of these to terrestrial origins or satellite reflections. The process demonstrated the potential for AI-assisted discovery. As datasets grow in complexity and size, computational tools will become essential for filtering noise and uncovering rare, potentially significant outliers. Simultaneously, the growing field of planetary protection is shaping how space agencies approach missions to potentially habitable worlds. This includes both forward contamination, the risk of bringing Earth microbes to other celestial bodies, and backward contamination, the risk of bringing alien material to Earth. Current planetary protection guidelines require sterilization of spacecraft components, trajectory planning to avoid unintended impact, and the isolation of returned samples. These policies are not just procedural. They reflect ethical considerations about preserving the integrity of alien ecosystems and safeguarding Earth's biosphere. The philosophical dimensions of life detection are profound. The discovery of alien life would challenge centuries of thought about uniqueness, creation, and the structure of reality. It would shift human identity from a singular biological experiment to one of many, embedded in a cosmic network of evolutionary pathways. Religious and cultural worldviews would be tested, reinterpreted, or expanded. For some, it would inspire awe and humility. For others, it might evoke fear or resistance. Already, some theologians and philosophers have begun preparing ethical frameworks for contact scenarios. Should we treat microbial life on another planet as sacred, protected from exploitation? Would intelligent beings, if encountered, possess moral status or rights? These questions, once speculative, are now being addressed in scholarly journals and interfaith dialogues. In recognition of the fact that discovery may occur not in the distant future, but within the span of current generations, this cultural preparation also includes the arts, which have long explored the implications of alien life. From literature to cinema to visual art, speculative fiction serves as a lens through which society examines its hopes, anxieties, and curiosities. These narratives shape public expectations, for better or worse. They can inspire interest in science or foster unrealistic assumptions about extraterrestrial behavior and technology. Managing these expectations, tempering imagination with empiricism, is an important task for science communicators and educators. Education itself is adapting to this new landscape. Curricula in astrobiology, planetary science, and exoplanetology are becoming more common at universities worldwide. Interdisciplinary programs encourage students to think across the boundaries of geology, biology, chemistry, and astronomy. The goal is not only to produce specialists, but to cultivate thinkers who can interpret signals, assess planetary environments, and build frameworks for unknown possibilities. In parallel, national and international policy is evolving. The discovery of alien life, even in microbial form, would prompt the activation of treaties, contingency protocols, and emergency coordination frameworks. The Outer Space Treaty of 1967, which prohibits the appropriation of celestial bodies by any one nation, provides a legal foundation, but it was not designed with life detection in mind. As such, spacefaring nations and global institutions are now considering amendments and expansions that address the biological, ethical, and legal consequences of discovery. If humanity were to encounter a signal unmistakably artificial, a structured pulse of radio waves from another star system, repeating, with mathematical precision, the response would unfold in stages. First would come verification, involving multiple observatories and independent confirmation. Next would be containment, with scientists and governments determining how to interpret, translate, or respond. Then would come dissemination, the controlled release of information to the public, along with the inevitable surge of excitement, speculation, and misinformation. In the absence of a signal, however, science remains methodical. It continues to scan, analyze, simulate, and hypothesize. Each exoplanet discovered, each spectrum analyzed, each mission launched contributes a thread to a larger fabric. A slow weave of understanding stretched across cosmic scales. The fact that we have not yet found alien life does not indicate its absence, but rather the infancy of our methods and the immensity of the universe. The Milky Way alone contains over 100 billion stars. Statistical models suggest tens of billions of potentially habitable planets. And our telescopes have only begun to scratch the surface. In this light, the silence of the skies is not discouragement, it is invitation. It reminds us that discovery is not a moment, but a process. That the universe does not reveal its secrets all at once, but over time, to those who listen carefully. In this age of interstellar curiosity, science is our vessel, and curiosity our compass. The search for alien life, whether it culminates in discovery or not, is among the most important scientific endeavors of our time. Not because of what it might find, but because of what it represents: a commitment to inquiry, a reverence for life, and a belief that the universe is more than what we can already see. The possibility of alien life carries with it an immense scientific weight, but it also bears philosophical gravity that stretches beyond data and observation. To ask whether life exists elsewhere is to question the nature of life itself, its emergence, its boundaries, its persistence, and its meaning. As such, the search for extraterrestrial biology becomes a kind of existential cartography, mapping the dimensions of what it means to be alive in a universe that is vast, ancient, and mostly silent. Life on Earth is defined by its organization, its metabolism, its ability to evolve and replicate. These traits are familiar and measurable, yet they may only represent one particular implementation of a broader principle, somewhere beyond the reach of current instruments. Alien chemistries may operate on different solvents, different metabolic pathways, and perhaps entirely unfamiliar forms of organization. The search, therefore, must accommodate not only what life is, but what life could be. This perspective has given rise to the idea of agnostic biosignatures, indicators of life that do not presuppose a specific biochemistry. Instead of searching solely for carbon-based organics or Earth-like gases, researchers are exploring the possibility of detecting complex, non-random structures, energetically sustained disequilibria, or repeating temporal patterns in planetary data. These indicators could suggest systems that are alive in function, even if their structure and composition differ radically from terrestrial models. For instance, certain chemical systems under continuous energy input may exhibit behaviors reminiscent of life, self-organization, compartmentalization, or molecular replication. Laboratory studies have already shown how non-biological systems can mimic some of life's features, prompting scientists to develop broader criteria for life detection. Rather than asking whether a molecule is biological, they might ask whether it performs functions associated with information storage, catechesis, or adaptive response. This approach is particularly useful for missions targeting environments that challenge Earth-centric assumptions. Venus, with its thick sulfuric acid clouds, extremely high surface temperatures, and crushing atmospheric pressure, was once deemed entirely inhospitable. However, The detection of trace gases like phosphine in its upper atmosphere renewed interest in the planet's potential for microbial aerial life. Organisms suspended in relatively temperate altitudes adapted to acidic aerosols, while the phosphine detection remains unconfirmed. It serves as a model for how surprises may emerge from unexpected corners of the solar system. Similarly, the mysterious behaviors observed in some exoplanetary systems have fueled speculation about advanced technologies or large-scale engineering. While natural explanations are always the starting point, the theoretical existence of Dyson spheres, massive structures built to harvest stellar energy, illustrates the kind of megastructures that might, in principle, be observable. Unusual dimming patterns, infrared excesses, or orbital anomalies could signal either exotic astrophysics or something constructed. These ideas extend the notion of technosignatures beyond communication into the realm of planetary-scale engineering. If a civilization alters its atmosphere for industrial purposes, reshapes its environment to suit its needs, or constructs energy-harvesting infrastructure, those changes may be detectable from afar. But here again, caution is paramount. Natural processes can often mimic artificial ones, and the burden of proof lies in ruling out all known non-biological mechanisms. Despite these complexities, the search persists because of the enormity of the stakes. The existence of alien life would profoundly reshape biology, showing that life is not an anomaly, but a statistical certainty given the right conditions. It would lend support to theories about life's inevitability in the universe and provide new branches of evolution to study. Microbial life, in particular, would serve as a second data point for comparative biology, potentially unveiling alternative biochemistries or evolutionary strategies. But the implications of intelligent life would be even more significant. Contact with a technological species, even if only through passive detection, would represent a fundamental moment in human history, one that recasts humanity not as the pinnacle of cognition, but as one node among many in a galactic web of awareness. The knowledge that others have achieved technology, survived cosmic hazards, and potentially endured for millennia would alter our understanding of possibility. In contrast, the continued silence of the universe also has consequences. It suggests that intelligence may be rare, that civilizations may be evolved, or that the galaxy is a quiet forest of cautious observers. The Fermi paradox. Why we have not yet seen signs of extraterrestrial intelligence despite the high probability of their existence remains unresolved. Its proposed answers range from sociological theories to filters embedded in the laws of biology or physics. Some posit that technological civilizations tend to self-destruct shortly after reaching a certain level of advancement, falling victim to ecological collapse, warfare, or runaway artificial intelligence. Others argue that the problem is communication. Civilizations may use technologies or languages fundamentally incompatible with our detection methods. Some even suggest that advanced beings choose not to communicate, preferring observation or non-interference with emerging species. These scenarios underscore the importance of preparing not only scientifically, but also psychologically and culturally. The impact of discovering intelligent life, or confirming its absence, requires mature frameworks for understanding, dialogue, and reflection. It also demands global cooperation, as the implications transcend national borders and individual disciplines. As such, a quiet revolution is taking place in how science engages with the unknown. Astrobiology is now an established academic discipline, supported by major institutions, funded by space agencies, and integrated into planetary missions. Its questions, once considered speculative, are now seen as essential to understanding the nature of the universe and our place within it. Furthermore, the tools of discovery are becoming more powerful, more precise, and more collaborative. The James Webb Space Telescope is already setting new standards in infrared observation. And missions like the Nancy Grace Roman Space Telescope and the European Plato Observatory promise to expand our knowledge of habitable zone planets. Future proposals envision interferometers in space, planet-hunting fleets, and even interstellar probes propelled by light sails. On Earth, observatories are refining their ability to monitor biosignature gases with ultra-sensitive instruments, while laboratories continue to model prebiotic environments to test theories of abiogenesis. Machine learning tools are being trained on exoplanet datasets to classify atmospheric compositions and identify outliers. Public data repositories make these resources available to researchers around the world, democratizing discovery and encouraging transparency. These efforts form a kind of scientific symphony, an intricate, multi-instrument exploration of a question older than recorded history. Whether the answer lies beneath an icy crust, in the clouds of a super-Earth, or in a signal from a distant star, we are laying the groundwork now. The instruments, the models, the missions, the philosophy, all of it converges on one question: is there anyone else? Yet, this question need not wait for an answer to be meaningful. The search itself expands our understanding, not only of the cosmos, but of ourselves. It teaches us to look carefully, to think broadly, to question assumptions, and to find beauty. In the unknown, it asks us to imagine the unimaginable, to empathize with the unfamiliar, and to care for the only life we currently know, our own. We look outward not just to find life, but to learn how to preserve it, to understand what makes a planet thrive, to see Earth not as the default, but as the result of a rare and fragile convergence. The search for alien life is also the search for planetary wisdom, a quest to understand how life begins, how it endures, and what it means to be a part of the universe. As exploration and observation deepen, the conversation surrounding alien life increasingly includes the idea of cosmic perspective. Not merely the awareness that we are small in a vast universe, but the realization that our moment in cosmic time may be both precious and precarious. It is a perspective forged through data, grounded in telescopes and landers, but also saturated with wonder. Every new planet found, every molecular fingerprint recorded, becomes a footnote in a growing chronicle of planetary diversity and potential. Within this expanding archive, the patterns begin to emerge. Some exoplanets display atmospheres rich in hydrogen or carbon dioxide. Others may have clouds composed of molten metals or silicate grains. Some orbit bright, stable stars. Others are locked in gravitational tides that yield permanent day on one side and endless night on the other. Despite this variety, the recurrence of certain types, rocky planets in temperate zones, gas giants at distant orbits, suggests that planetary formation, though complex, follows statistical rhythms. And within those rhythms, life may arise not as an exception, but as a frequent improvisation on cosmic themes. Such realizations shift the emphasis from searching for rare miracles to identifying universal mechanisms. Scientists now investigate the likelihood that life emerges when specific criteria are met: stable temperatures, the presence of liquid solvents, a continuous energy gradient, and time. If these ingredients are present long enough and with enough variation, then perhaps life is a consequence of chemistry under pressure. In this view, the universe is not merely habitable, it is bioactive, tending toward complexity wherever the conditions allow. Laboratories across Earth simulate these conditions in sealed flasks and hypershore chambers. Researchers recreate the atmospheres of early Earth, of Venusian clouds, of Martian regolith. They introduce energy through light, heat, or electrical discharge and observe as molecules organize, interact, and sometimes self-replicate. These prebiotic simulations, building on the foundational milliuria experiments of the 20th century, aim to bridge the gap between non-living and living systems. They seek to understand how matter crosses the threshold into metabolism and memory, What they reveal is not a single pathway to life, but many. Life, it seems, does not require exact replication of Earth's conditions. It requires dynamics, changes, interactions, systems far from equilibrium. From these dynamics, structure can arise. And structure, once capable of preserving itself, begins the journey toward biology. In this view, life is not a singular event, but an emergent property of matter under constraint, a phenomenon that may be common even if its expressions are endlessly diverse. As theories of origin evolve, so too do definitions of life. It is no longer sufficient to define it by carbon, water, or DNA. Some researchers propose definitions based on thermodynamic boundaries, information retention, or systemic self-production. Others advocate for functional descriptions, systems, that react to stimuli, sustain themselves, and evolve through selection. These broader definitions are designed to detect life that might not mirror Earth, including life based on alternative chemistries or residing in environments unlike any we know. These shifts have deep implications for exploration. Future missions may no longer search solely for water or Earth-like gases, but for patterns in entropy, for symmetry-breaking processes, for long-term energy usage inconsistent with geology. The instrumentation itself must adapt, capable of sensing unfamiliar molecules, interpreting ambiguous data, and rejecting assumptions rooted too firmly in terrestrial biology. Already, mission planners are incorporating these principles into payload designs, ensuring that new probes and rovers can identify life as function, not just as form. Another frontier lies in the detection of temporal signals. Life is not static. It pulses, fluctuates, cycles. Earth's biosphere produces seasonal variations in gas composition, surface reflectance, and thermal output. By observing similar periodicities on distant planets, scientists may infer the presence of biological cycles, plant growth, atmospheric respiration, or even migration. These time-dependent biosignatures offer another layer of inference, especially when paired with spatial data and spectral analysis. Temporal data also apply to technosignatures. An artificial signal might blink on and off, repeat at exact intervals, or shift in frequency in a way that natural sources cannot replicate. Modulated signals, non-random polarization patterns, or recursive transmissions could all serve as evidence of technological origin. Even a single pulse, if highly structured and localized, might warrant investigation. Yet each must be filtered through rigorous analysis to rule out terrestrial interference, satellite, crosstalk, or instrument malfunction. This rigorous skepticism is not meant to deny the possibility of discovery, but to preserve its integrity. Astrobiology's greatest challenge is not false hope, but premature conclusion. In a field where claims echo globally within seconds, the cost of error is high. As such, each detection is scrutinized not once, but repeatedly by teams working across continents, disciplines, and languages. Peer review, replication, and transparency are not hindrances. They are the tools that transform curiosity into science. Alongside this technical framework exists a social one. The search for alien life is not conducted in isolation. It is shaped by culture, history, and collective imagination. Different civilizations throughout human history have viewed the cosmos as divine, mechanical, infinite, or cyclical. The modern scientific paradigm sees it as a realm governed by discoverable laws within which life may be one of many outcomes. But even now, public response to extraterrestrial discovery would unfold through lenses of religion, politics, and philosophy. To prepare for this, researchers have begun modeling psychological and sociological reactions to discovery. Studies suggest that while initial responses might include shock or fear, long-term reactions often trend toward curiosity, integration, and wonder. The idea of not being alone, once internalized, reshapes identity and purpose. It calls into question, the primacy of human intelligence, and invites a reevaluation of ethics, coexistence, and cosmopolitanism. Moreover, the very act of searching alters how humans behave. It fosters collaboration across national borders. It encourages interdisciplinary thinking. It trains a generation of scientists to be comfortable with ambiguity, patient with progress, and open to mystery. In this way, the search for alien life becomes more than a quest. It becomes a discipline, a philosophy, and a lens through which to view our own species. As space agencies and private entities invest in deeper missions. Toward Europa, Titan, exoplanetary spectroscopy, and interstellar signal processing. Each effort brings us closer to clarity. But perhaps the most profound outcome will not be the signal or the microbe or the artificial light curve. Perhaps the most profound outcome will be the reshaping of human consciousness, grounded in data, lifted by imagination. The search for alien life teaches patience. It demands humility. It operates at the speed of light, but unfolds over decades. It is, in many ways, the opposite of immediate gratification. And yet, it thrives, fueled by hope, anchored in evidence, and driven by a question that has survived every era, every revolution, every paradigm shift. That question, are we alone? It's never been answered, but it has never been abandoned. It rises with every launch, it blinks with every telescope image, and it rests in the silence between stars. And as long as that question remains alive, so too does the spirit of exploration. In the vastness of cosmic silence, the pursuit of alien life becomes a dialogue between speculation and observation, between the past that shaped Earth and the futures we can only imagine. It is a journey through data, dust, gas, light, and logic, seeking not only organisms but stories. Stories written in chemistry, temperature, orbit, and time. The last decade has shown that our planet is not a solitary miracle, but one among thousands of potentially habitable worlds. And still, as our sensors become more refined and our theories more sophisticated, the ultimate answer remains elusive. This ambiguity is not failure. 'Tis the defining condition of a mature science. In astrobiology, as in all fields at the boundary of the known, progress often lies in sharpening questions rather than rushing toward conclusions. Each new planetary candidate, each unexplained anomaly, each spectroscopic pattern pushes the edge of understanding outward. Slowly, the picture comes into focus, not always in the form of a signal or a microbe, but in the scaffolding of knowledge itself. Perhaps in some far corner of the galaxy, life flourishes quietly beneath an icy crust. Perhaps it blooms in ammonia seas or drifts through methane clouds. Perhaps it is intelligent, cautious, and aware, but distant by millions of years, unreachable not by space but by time. Or perhaps life is common but fragile. Perhaps biospheres flicker like candles, lit often but extinguished just as easily. Victims of shifting stars, unstable climates, or internal self-destruction. These possibilities carry weight not only for discovery, but for stewardship. If Earth is rare, not because life is rare, but because persistence is, then our obligation is enormous. The same insight that drives us to search also demands that we protect the only biosphere we know. The better we understand planetary fragility, the more urgently we must address climate change, biodiversity loss, and ecological collapse. Earth becomes not just a cradle of life, but a prototype, a system whose survival teaches us how to find and preserve others. Astrobiology does not end with detection. It continues through interpretation, integration, and response. What do we do if we find a microbial biosphere on Europa? Do we drill deeper or leave it untouched? If we intercept a signal from a civilization 1,000 light-years away, do we reply or listen indefinitely? And if we discover that we are, in fact, alone, does that instill despair or reverence? These are questions without equations, without definitive answers. They belong not to physics or biology alone, but to all of human culture. The societal preparation for discovery is already underway. Books, films, essays, and simulations help shape the global narrative. SETI protocols outline how scientists might verify and report evidence. Ethics committees explore what counts as responsible contact. Philosophers debate the rights of alien microbes and the obligations of technological species. Artists imagine new constellations of meaning. This collective preparation reflects a truth at the heart of the search, that the discovery of alien life would not be the end of a story, but the beginning of a new one. And still, the methods of science continue with relentless care. Data sets grow, missions are planned. Observatories scan stars by the millions. Chemical signatures are modeled. Laboratories simulate prebiotic oceans and high-altitude balloons. Probe stratospheres. Each of these efforts adds a pixel to the cosmic portrait. No single discovery will likely deliver a definitive answer. But across time, across disciplines, a pattern may emerge, one that slowly, clearly suggests that we are not the only instance of biology, not the only mind turned upward in wonder. When that realization comes, if it comes, it will arrive not with certainty, but with probability. Not with headlines, but with curves, statistics, and confidence intervals. It may not come in the form of "they are here," but in a graph showing unexpected oxygen levels on a far-off world. It may be debated, revised, and resisted. But its power will lie not in its drama, but in its truth. That in a universe of darkness and distance, something else lives, or once lived, or will live again. And if the silence holds, if no signal comes, no spectroscopic curve betrays an exoplanet secret, no geyser whispers of microbes in alien oceans, then even that is a kind of answer. It tells us that life is precious, that civilization is fragile, and that we carry an extraordinary responsibility to listen harder, to protect what we have, to imagine new futures. Whether the answer lies in light from a distant sun or under Europa's ice, in radio waves or in the residue of unknown chemistry, one truth is already clear. The search itself is a reflection of humanity's highest qualities: our curiosity, our humility, our courage to ask questions without easy answers. In the search for alien life, we discover ourselves more fragile, more interconnected, more capable than we once believed. Thank you for watching this journey with the Sleepless Scientist. If we've disturbed your sleep with thoughts of alien microbes or faraway worlds, we sincerely apologize. But if we've sparked a sense of wonder, a curiosity that transcends time and space, then perhaps it was worth it. Please consider liking this video, sharing it with fellow stargazers, and commenting with your location and the time you're watching, whether from the quiet side of midnight or under a morning sky filled with possibility. Now, let your thoughts dissolve into the vastness of the cosmos. Let the sounds that follow wrap you like a blanket of starlight. No more words, only silence and the subtle hum of existence. Breathe in the calm. And as you drift into sleep, know that the universe continues, expanding, unfolding, inviting. Good night.